Hi everyone, and welcome to the School on Spectral Methods for Complex Systems. My name is Massimiliano Lupo Pasini. I am a postdoctoral research associate at Oak Ridge National Laboratory, but today I'm going to talk to you about some work that I developed during my PhD studies. In particular, during my doctorate studies, I focused on numerical linear algebra for the analysis and the development of new algorithms to solve sparse linear systems in parallel. As you may already know, solving sparse linear systems is very solving sparse linear systems efficiently is very important because linear systems arise from many real-life applications like electronics, computational fluid dynamics, structural engineering, since all these fields of studies require the analysis and the solving of partial differential equations that can be discretized and treated by computer through discretizations like Galerkin methods, finite differences, or finite volumes. Any of these different types of discretizations for the PDE leads to a linear system or a sequence of linear systems that need to be solved numerically and so via computer. Moreover, real-life applications require models that are more and more complex to reproduce in a more and more reliable way the reality that is surrounding us. And this means coming up with linear systems with an increasing number of unknowns, and therefore the complexity of the linear systems that need to be solved leads the computer manufacturer to increase the capacity of upcoming computers in order to meet the new requirements for the new applications. This also means that state-of-the-art linear solvers cannot address new high-performance computing issues arising from new computers that are built with an increased complexity, and therefore the need to focus on new linear solvers. In particular, during my PhD project, I focused on deterministic and stochastic acceleration techniques for Richardson-type iterations. This was a joint work with my PhD advisor, Professor Michele Benzi, at Emory University, Department of Mathematics and Computer Science, and also in collaboration with Thomas Evans, Stephen Hamilton, Stuart Slattery, and Fanish Suryanarayana. The U.S. Department of Energy Office of Science gave us research funds to conduct this kind of studies. And my presentation will be split in two lectures of 1 hour each. In the first part, I will, of course, reiterate the reason why we wanted to study deterministic and stochastic accelerations for Richardson-type iterations. And then I will focus onto the deterministic acceleration, the so-called Anderson acceleration. I will show you some results presented in the mathematical literature, and then I will dive into a new algorithm that has been recently proposed by Fanish Suryanarayana and collaborators, and some theoretical results that I developed in my thesis in this respect. The second part of the presentation, the second lecture, will focus instead on the stochastic accelerations via Monte Carlo approaches. So, as I already mentioned, there's a strong need of new and efficient and reliable algorithms to solve highly dimensional sparse linear systems that are moving towards exascale in a parallel computing framework. In particular, computer manufacturers try to meet the requirements of new applications by increasing the computational complexity and the computational power of supercomputers by increasing the number of nodes that compose the computing network. This, of course, means also leading to new challenges, such as the cost of the communications. Indeed, increasing the number of nodes in the computing network means increasing the cost required to allow communication between the different nodes that compose the computer and that need to communicate with each other to progress in the computation. Moreover, um, on the other hand, we also have an increased occurrence of faulty phenomena. Where for faulty phenomena, we refer to an abnormal condition that can cause the computer to deliver a wrong answer. Um, on the side of faulty phenomena, we can classify faults as hard faults or soft faults. Hard faults are related to a power loss or the crash of a computing node, and in that case, the computing node stops contributing in the computation. The soft faults instead is more difficult to detect because it can be related to a bit flip, and this means that the computing node will progress in the computation but generating wrong data. In general, there's the need, on the one hand, to develop algorithms that are efficient in reducing the communication and therefore reducing the computational overhead, which means communication prevailing over computation. And on the other hand, there's also the need to cope with faulty phenomena that are inevitable. And so there's the need to build resilient algorithms that are robust against these abnormal conditions. In the first part, for the deterministic acceleration, we will focus on efficiency, and so reduction of the computational time. An algorithm running in parallel is guaranteed to perform efficiently if it is scalable. And scalability is the capability of an algorithm to handle a growing amount of work. Growing amount of work on linear systems means growing amount of unknowns. So as the size of the linear system to solve increases, we need an algorithm that is able to cope with that increasing size, capping the computational time required to attain a prescribed accuracy. During the years, different contributions have been given on different paths to come up with scalable algorithms. And the most explored path was the one that tried to adapt Krylov subspace methods to increase the scalability of this technique by reducing the communication required via communication avoidance strategies. Some techniques, for instance, were obtained via block versions of Krylov subspace methods or S-steps method. And you have some references in slide number 6 if you want to explore more in this respect. However, another possible scenario can be represented by starting with simpler methods like relaxation sweeps and try to improve the performance of these methods by accelerating them. The reason why relaxation sweeps can be considered as an alternative to Krylov subspace methods is because relaxation sweeps indeed are very simple schemes that exploit data locality, and therefore the data locality of the needed for relaxation sweeps can leverage the parallelization, controlling, capping the communication required to perform the computation. And actually, the acceleration of relaxation sweeps is going to be the focus of these two lectures that I'm going to deliver. At first, starting from slide number 7, let's settle the mathematical framework. Our interest is a sparse non-singular linear system as the one shown in equation number 1, ax equal to b, where A is supposed to be a sparse non-singular matrix, X is the solution vector that needs to be computed, and B is the right-hand side. Now, assuming that a possible left preconditioning is incorporated in the notation of formula number 1, we can then recast the linear system at equation number 1 as a fixed point scheme as shown in equation number 2, where x is equal to h times x plus b. H is the iteration matrix and is equal to the identity minus the coefficient matrix A. The fixed point scheme is known to converge to the exact solution of the linear system in equation number 1 if and only if the spectral radius of the iteration matrix is less than 1. However, sometimes fixed point iterations are characterized by a deteriorated convergence rate, an asymptotic deteriorated convergence rate. What this means is that as the iteration index progresses, the accuracy of the solution becomes less and less significant. And therefore, sometimes the number of iterations needed to attain a prescribed accuracy through a fixed point scheme is too high. And therefore, the computational time becomes too long. This leads to the need of accelerating fixed point iterations via via some techniques that in literature are known as multi-level methods. The idea behind the multi-level methods is to accelerate the fixed point iteration by alternatively using the original linear system and a hierarchy of reduced linear systems. The way the hierarchy of reduced linear systems is constructed is based on the identification of a projection subspace. Different multi-level methods have been developed according to the way the projection subspace is constructed. And indeed, multi-level methods differ from each other for the projection subspace that is adopted. On the one hand, we have aggregation methods like multigrid methods, where the idea is to cluster, agglomerate multiple unknowns into a single scalar. So clustering multiple values into a single value allows one to reduce the size of the linear system, building therefore a sequence, a hierarchy of linear systems of smaller size with respect to the original one. Geometric multigrid methods, for instance, are based on the geometry of a mesh, of a grid, and the idea is to start from a very refined mesh and coarsen it so that the linear system associated with the very fine grid can be reduced and associated with the coarser mesh. However, some other types of multigrid methods, like algebraic multigrid methods, try to adopt a similar technique for situations where a mesh or a grid is not provided or is not known. In that case, the reduction of the linear system of interest is applied via the adjacency graph associated with the coefficient matrix. In particular, the adjacency graph is simplified by collapsing adjacent nodes into a supernode. and the collapsing of multiple nodes of the graph into a single one allows one to simplify the complexity of the graph and therefore allows one to reduce the size of the linear system. A possible alternative to aggregation methods is represented by minimization methods. In this case, the identification of the projection subspace is not carried out via geometrical reasonings or reasonings based on adjacency graphs, but it's actually based on the satisfaction of an optimality criteria. And minimization methods are the type of multi-level methods that I will focus from now on to accelerate relaxation sweeps. In particular, minimization methods operate additively. What additively means in this case is that the solution at an iteration k is provided as the solution at the previous iteration k minus 1 plus an additive term, a correction. For instance, if we start considering the fixed point scheme as shown at the very first formula in slide number 9, we know that we can recast the fixed point formula as a corrective formula, as a corrective representation. The corrective representation is xk minus 1 plus rk minus 1, where rk minus 1 is the residual computed at the previous step. The passage from the first formula to the second one is possible exploiting the fact that h is equal to I minus a. And in this case, an acceleration for a fixed point scheme can be introduced additively as shown in formula number 3, where the solution at the step k is additively corrected by u sub k times g sub k to form a new approximate solution xk bar. And the correction uk times gk is provided via building a matrix u sub k that is supposed to be rectangular and that has p columns. The number of columns of the matrix u sub k represents the dimensionality of the projection subspace onto which the correction is computed. And g sub k is nothing but a linear combination of the columns of U in order to identify a correction that satisfies an optimal criteria. In particular, among all the possible minimization methods, the Anderson mixing is an option. And usually Anderson mixing is utilized to accelerate non-linear fixed point iterations. However, Anderson himself, in his very early publication in 1965, already mentioned the possible benefit that Anderson mixing could provide also to linear fixed point iterations. The Anderson mixing is a specialization of formula number 3 by specializing the matrix U sub k so that every column of the matrix U sub k is the difference between approximate solution computed at successive iterations. This allows then to rewrite formula number 3 as shown at the very bottom of slide number 10. Here I'm explicitly using the specialization of the matrix U sub k to express U sub k times g as a linear combination of the columns of U with respect to the coefficient g. How the vector g is computed depends on the optimality criteria that one person wants to satisfy. The Anderson mixing, in particular, requires the optimal criteria to be the minimization of the residual. Therefore, the vector G sub k is supposed to be the vector that minimizes the residual associated with the linear system of interest onto the projection subspace identified by the columns of the matrix U. At the very center of the slide number 11, we have indeed the representation of a least square problem, where the matrix X sub k is equal to the matrix U flipped by sign, and then we have the matrix capital R that is minus A times capital X. The representation of the least square problem as at the very center of slide number 11 holds only assuming that the matrix R has full column rank. This is not needed computationally speaking because the algorithm can still work even if the matrix doesn't have full column rank, but I will use anyway this mathematical representation very often during the presentation for mathematical convenience and also for ease of representation. Anderson himself proposed an algorithm to accelerate the Richardson iteration via the Anderson mixing. And indeed, the method that he proposed is called Anderson-Richardson method. The Anderson-Richardson method is called this way because the idea is to alternate an Anderson mixing with a Richardson step, an Anderson mixing with a relaxation strip. The Anderson mixing is shown in formula number 5 in slide 12, whereas equation number 6 represents a relaxation sweep. And the idea is to alternatively switch between 5 and 6 up until a prescribed accuracy is obtained. Anderson-Richardson can indeed be considered as a multi-step method, where equation number 5 is an acceleration and equation number 6 is a relaxation. So we can see the connection between this specific type of multi-level method and the general case of a multi-level method when the solution associated with the original big linear system of interest is combined with the solution of a smaller linear system related to a projection subspace. Equation 5 and 6 can also be combined altogether in equation as shown in equation number 7. Sometimes this notation can be convenient for mathematical studies because equation number 7 highlights the fact that Anderson-Richardson can be recast as a non-stationary Richardson as shown in equation number 8. And the matrix C sub k has a very complicated structure as shown in number 9. And from now on, we can say that Anderson-Richardson can be implemented in different ways according to how the user decides to select the value P. P, remember, is the size of the projection, is the dimensionality of the projection subspace. If one person decides to increment P according to the iteration index, then we will refer to that version of the method as full Anderson-Richardson, full AR. If, on the contrary, the user decides to fix P to a specific value so that the number of iterates employed to identify the projection subspace is characterized by a sliding window, then in that case we will refer to truncated Anderson-Richardson or truncated AR for convenience. In literature, many people studied the behavior of Anderson-Richardson compared to the performance of the generalized minimum residual, shortly named GMRES. And people proved that full Anderson-Richardson loses generality with respect to full GMRES, because full GMRES is always guaranteed to converge on a non-singular matrix, whereas full Anderson-Richardson is only guaranteed to converge if the spectral norm of H is less than 1. Moreover, as shown in slide number 14, full GEM-REST and full AR are equivalent only in the absence of stagnation. This means that as long as no stagnations occur, full AR and full GEM-REST provide the same solution at each iteration in exact arithmetic. However, as soon as a stagnation occurs, full GEM-REST will recover from the stagnation sooner or later, but full AR will never recover from the stagnation, and it will never reach the prescribed accuracy to converge. This means that full AR doesn't represent an appealing alternative to full GEM-REST. In particular, it doesn't represent an appealing alternative in terms of what are the upcoming issues arising from new computing architectures. First of all, because still full AR is characterized by an increasing computational cost per iteration, because we still have to solve a least square problem per iteration in order to compute the Anderson mixing. Moreover, the size of the least square problem increases as the size of the projection subspaces expands according to the iteration index k. And this also means that solving a least square problem at each iteration overkills the parallelization, introducing severe bottlenecks. Therefore, we can say that full AR is not an algorithm of interest to address new computing challenges in a high-performance computing framework for solving linear systems. However, recently, Fanish Suryanarayana and collaborators introduced a new variant to combine Anderson mixing and Richardson iteration. In particular, they proposed the so-called alternating Anderson-Richardson. The idea, presented in slide number 15, is to intertwine multiple Richardson sweeps among two consecutive Anderson acceleration. So instead of alternating a Richardson sweep and an Anderson mixing, the idea is to combine multiple Richardson sweeps before computing an Anderson mixing. In another way, what this algorithm proposes is to relax or reduce the frequency with which an Anderson mixing is performed. Again, AAR can be recast as a non-stationary Richardson iteration as shown in equation number 10, and you can see that equation number 10 is actually equal to equation number 8, but in this case, the matrix C sub k attains different representations according to the iteration index. This is explained by the fact that at some iterations, only a relaxation sweep is performed, whereas at other iterations, an Anderson mixing plus a Richardson step are computed. In slide number 16, you have the pseudocode of the alternating Anderson-Richardson, and the key lines in this case are lines number 7 and 8, where the matrices capital X and capital R are built, and these matrices are essential to compute the Anderson mixing and to perform the least square problem. And another key line is line number 9. This if-else statement is essential because it allows the algorithm to understand whether a single relaxation sweep is needed or whether the relaxation sweep needs to be combined with an Anderson mixing, according to the iteration index. I also provide the pseudocode for the full GEM-REST, and the reason why I provide the pseudocode for the GEM-REST as well is because during my PhD project, I conducted a theoretical analysis for alternating Anderson-Richardson, and I tried to mimic in this analysis some steps that people in literature did for AR. So I tried to mimic what people did in the case of AR to conduct a theoretical analysis for AAR. And in particular, I will refer to some quantities that I introduced in slide number 18. The stagnation index is defined as the first iteration at which stagnation occurs. And for stagnation, I mean the first situation where the solution does not change between consecutive iterations. Moreover, the grade of R0 with respect to A is defined as the index at which the dimensionality of the Krylov subspace doesn't increase anymore. During my studies, I proved a theorem shown in slide number 19, where I essentially succeed in demonstrating that full AAR and full GMRS are periodically equivalent in absence of stagnations. Periodically equivalent means that every time an Anderson mixing is performed, that is, every time a least square problem is solved, then full AAR provides the same solution as full GMRS for a specific iteration index, and assuming that no stagnations occur. The equivalence between AAR and GMRS does not occur at each iteration, but it only occurs periodically because a least square problem needs to be solved in order to restore the equivalence. And the least square problem is performed only when the Anderson mixing is computed. The next natural question is wondering what happens to the equivalence between these two algorithms if the stagnation occurs. The situation in this case is slightly more complicated than for AR. We know that Anderson-Richardson will never converge if a stagnation occurs. For alternating Anderson-Richardson, the situation is better, in the sense that alternating Anderson-Richardson succeeds in recovering from a stagnation, assuming that the stagnation doesn't last too many iterations. In particular, in figure number 2, I provide you with a schematic representation of what happens. The vertical lines represent the iterations. In particular, thick blue lines represent iterations where an Anderson mixing is performed, whereas thin black vertical lines represent the iterations where a simple relaxation sweep is computed. And the horizontal red lines represent the extension of a stagnation. Therefore, iterations spanned or crossed by the red line represent stagnations at which the approximated solution doesn't improve. Alternating Anderson-Richardson succeeds in recovering from the stagnation for situations number 1 and number 2, because in this case, two consecutive Anderson mixing are performed on projection subspaces that succeed in expanding, and therefore expanding the dimensionality of the projection subspace. It is possible to improve the solution by exploring and minimizing the residual on an expanded subspace, whereas in the situation number 3, the stagnation lasts too long. Therefore, two consecutive Anderson mixing are computed onto the same projection subspace that is not expanded, and this causes an eternal stagnation from which AAR will never recover. This scheme is also mathematically reformulated in theorem number 2 of slide number 21. I understand that there are many details to go through, and for this, I encourage you to send me emails or to ask me questions in case you don't understand anything. I can also provide you with a PDF of my PhD thesis where these algorithms and the theoretical analysis is explained in way more details. So if we want to compare Anderson-Richardson with this novel technique called alternating Anderson-Richardson, we can understand and we can definitely say that alternating Anderson-Richardson represents an improvement because full AR wouldn't be able to recover from any type of stagnation. Type 1, Type 2, and Type 3 would represent lethal stagnations for AAR, whereas alternating Anderson-Richardson has an improved robustness in the sense that AAR succeeds in recovering from Type 1 and Type 2 stagnations, whereas only Type 3 is represented as a critical situation from which convergence cannot be obtained. In order to validate the improved robustness of AAR with respect to AR, I provide you with, in slide number 23, with the recipe to construct an ad hoc numerical example where you're going to build a matrix that has a block structure, and every block is made of a circulant matrix. And circulant matrices are renowned to cause stagnation in GMRES. And they will cause also stagnation for full AAR. And the reason why I build this problem where the matrix as a block structure with blocks of increasing size is because I want you to show and I want you to verify that if that eventually you will see full AAR periodically stagnate, but eventually converge to the solution of the linear system of interest at the prescribed accuracy. If you have questions about how to construct this numerical example, in case you don't understand it, please get in touch with me, and I will be more than glad to help you out figuring out what to do. Another thing to keep in mind is that alternating Anderson-Richardson and the GMRES construct different bases to produce the same projection subspace. As you know, a Euclidean subspace can be constructed using different bases. And for instance, if you think about R3, a three-dimensional Euclidean subspace, you can use the canonical basis made of 1, 0, 0, 0, 1, 0, and 0, 0, 1, or you can use any other arbitrary ternary of vectors like 1, 1, 0, 0, 1, 1, 1, 1, 1. The canonical basis and this new set of vectors, they both reproduce the entire three-dimensional Euclidean subspace, but the two bases are actually different. And this is exactly what happens between alternating Anderson-Richardson and the GMRES. They construct the same projection subspace every time an Anderson mixing is computed, but the bases are different. This is very important to remember because if a person wants to truncate the bases and reduce the size of the window employed to construct the projection subspace, what happens is that the equivalence between AAR and GMRES is lost. Full AAR and full GMRES are equivalent in absence of stagnation. But since the two bases employed are different, the truncated version of AAR and GMRES are not equivalent anymore. And this is explained in slides number 24, 25, and 26. Now, going back to the case of the non of the lack of a full rank matrix, as if you remember when I explained the concept of Anderson mixing and least square problem, I referred to RK transpose RK inverse, RK transpose trumps the residual as a way to compute the solution to the least square problem. This coincides with explicitly building the normal equation, and of course, usually this is not done. Indeed, in my code, I implement the algorithm by solving the least square problem with the QR factorization with column pivoting, as MATLAB suggests. And solving a least square problem with the QR doesn't require at all the matrix R to be full rank. Indeed, through many numerical examples, I experienced that in some situations, the matrix R doesn't have full column rank, but this doesn't prevent convergence. This doesn't hinder convergence at all, and still convergence can be attained. Moreover, I also succeeded in proving that alternating Anderson-Richardson in whatever version you want to use, full or truncated, is guaranteed to converge if the spectral norm of the iteration matrix is less than 1. This is a result very similar to the one that Tim Kelly and his collaborators published in a paper, and you will find details about this paper in the bibliography associated with this presentation. Another question that my advisor and I wanted to address was to identify classes of problems for which the truncated version of AAI is guaranteed to converge. As you may already know, this is something that already happens in GMRES. Indeed, full GMRES is always guaranteed to converge in exact arithmetic. However, the restarted version of GMRES is not always guaranteed to converge. There are situations where restarted GMRES always stagnates without ever converging. But it can be proved that restarted GMRES always converges for positive definite matrices. So our natural questions was, can we reproduce a similar results for AAR? And we actually succeeded in doing that. Indeed, in my PhD thesis, I proposed a variant of AAR called augmented alternating Anderson-Richardson, AAAR, where the idea is to expand the projection subspace in order to include some useful vectors that can facilitate the convergence. And the vectors that I use are based on the same rationale that is used to prove the convergence of restarted GMRES on positive definite matrices. In particular, if you look at the proof on the book published by Joseph Saad called Iterative Methods for Linear Systems, the proof there, the essential, the turning point for the proof to work is to show that the subspace used by restarted GMRES contains the direction associated with the residual after solving a least square problem. So what I did was to expand the dimension, the subspace of the was to expand the projection subspace constructed by AAR so that I could include the residual as a direction as a direction to enrich the projection subspace. And by including the residual into the basis used to construct the projection subspace, I can prove that this augmented variant of AAR can converge always on positive definite matrices, as shown in theorem number 4. And this proof as well can be found in my thesis. I also considered numerical examples performed in MATLAB and here in slide number 32, you have the specifics about the different parameters. And the results that I'm going to present are averaged over multiple runs, where the solution is always computed as a random vector, and the right-hand side is computed as A times X. To visually represent the results, I use performance profiles, and the metric adopted is the time. So a method is supposed to perform better than another if it converges faster in less time. And in slides number 33 and 34, you have some specifics about how I set up the performance profiles. And the comparison between alternating Anderson-Richardson and GMRES is performed on a fixed set of problems and varying the preconditioner. At first, I use no preconditioner at all. Then I use a diagonal preconditioner. Then I use an ILU 0, and then I use an ILU t with the threshold equal to 10 to the minus 4. Let's first focus on use of no preconditioner. So this is the table representing the problems that I use. These are all problems taken from the Sweet Sparse Matrix Collection that was previously called University Florida Matrix Collection, or the Matrix Market Collection. And then there are three matrices called SP1, SP3, and SP5 that have been given to me by my collaborators from Oak Ridge, and they essentially represent the discretization of the Boltzmann equation that is used in nuclear engineering. So for no use of preconditioner, I compare augmented Anderson-Richardson with m equal to 6 and p equal to 12. M equal to 6 means that I use 6 Richardson sweeps between two consecutive Anderson mixing, and the sliding window used to build the projection subspace is equal to 12 iterations. And I compare the performance of AAR with restarted GMRES with the restarting parameter equal to 10 and 30. As you can see, the line associated with AAR is always above the ones associated with restarted GMRES. This means that AAR converges in average faster than restarted GMRES. Moreover, if you look at the far right of the graph, you see that at the very right, the line associated with AAR sits above the ones associated with restarted GMRES. The way you have to interpret this is by considering that AAR converges on problems where restarted GMRES doesn't converge. So AAR generalizes the set of problems that can be addressed. AAR converges on more situations, including situations where restarted GMRES doesn't converge at all. Similar behavior in figure number 2, when a diagonal preconditioner is used. And when an ILU preconditioner is used, you can see that the lines are lifted up, and this means that all the algorithms succeed in converging on a wider set of problems thanks to a better quality preconditioner. And if we improve the quality of the preconditioner with an ILU t, again, all the lines are lifted up. The distance between the lines is shortened. This means that the performance of restarted GMRES improves. However, at the very right of the graph, you can still see that there is a gap that cannot be filled. This means that, again, although the quality of the preconditioner is really good, there are still some situations where AAR converges, but restarted GMRES does not succeed in converging. I also ran some experiments in MPI using C as a programming language and using PETC as a numerical linear algebra library to use wrappers for matrices and vectors. In slide number 41, I give you a description of the specifics of the cluster that I used, and also specifics about the problems that I still pulled from the sweet sparse matrix collection. And in table number 42, I compare the performance of truncated AAR with restarted GEMRES, using different number of processes for each type of problem. And for Atmos model and circuit 5M underscore DC, the performance of the three algorithms is very similar. However, what's interesting is what happens for the last three test cases. Indeed, you can see that truncated AAR converges for Freescale 1, whereas restarted GEMRES doesn't converge at all. For Curve 4 and transport, AAR converges way faster than restarted GEMRES. So also with the MPI experiments, we can show that AAR improves the performance with respect to restarted GEMRES. In general, the idea of AAR is to improve the performance with respect to Anderson-Richardson by relaxing the frequency with which a least square problem is solved. Relaxing the frequency with which a least square problem is solved, in other words, increasing the number of Richardson sweeps between consecutive Anderson mixing, on the one hand, increases robustness against stagnations, and on the other hand, it also increases simplicity, and therefore it increases the parallelizability of the algorithm by reducing the communication required. All these results are going to also be published soon in a manuscript entitled Convergence Analysis for Anderson Type of Acceleration of Richardson's Iterations. This manuscript is currently under review, and I hope that I will be able to publish it as soon as possible. In conclusion, we can say that state-of-the-art algorithms strive to address efficiency and parallelism. However, preliminary promising results have been obtained with AAR. And in the future, also a deeper understanding of the algorithm and also deeper analysis and comparison with Krylov subspace methods is needed, and possibly also implementing a version of the code that exploits GPU accelerations. This is essentially the end of lecture number 1, and so this is the end of the deterministic acceleration, and lecture number 2 will start explaining the stochastic acceleration for the Richardson type iteration.